So we have this multiple regression model where I is equal to beta 1 plus beta 2 xi2 plus beta k xik plus every term I is run from 1 2 until n. Here, so now you should know that we actually have n equations here. Like y1 is beta 1 2 e1 y2 so on so for yn. Okay, let's define a vector y, stack y1, y2, yn together. So it's in by one vectors. E is e1, e2, en. Beta will be beta 1. So this is in by one vector or in by one matrix. Beta 1, beta 2, beta k. So it's k by 1 vectors. And xi will be equal to xi1, which is actually equal to 1. Okay. The constant term, the intercept. xi2 until xik. So it's k by 1 vectors. So this is the x for observation I. So then x, bigger x, is just x1 prime. Remember this prime is transpose. So for example, x1 is equal to x11, x12, x1k. So transpose x1 prime will be, here is k by 1 matrix. Then transpose will be 1 by k, so 1 row k columns, x11, x12, x1k. So that's what it means by transpose this prime. So first observation x1 prime, second x2 prime, so on and so forth, x n prime. Define this to be x, which is just x11, x12, x1k, x21, x22, x2k, xn1, xn2, xnk. So note that first column is all equal to 1, which corresponds to our constant terms. And this is n by k matrix. Okay. So given these quantities, we can now write our model more compactly as this y is equal to x beta plus e. Okay. So basically we're saying that y1, y2, yn is equal to x11, x12, 1k, k, n1, n2, nk times beta 1, beta 2, beta k plus e1, e2, ek. That's That's the compact way of writing our system in equations here. And I assume that you have fun with this linear algebra, the matrix operation, matrix multiplication here. So this is n by 1, this matrix is n by k, this is k by 1, so the multiplication is n by 1, and this is n by 1. So when we do matrix multiplication, addition, division, these matrices need to be comfortable of each other. Okay, so now we have this model. Y is x beta plus e, and we want our least square principle. We want to choose beta to minimize. Let's call this S, sum of square error. Square, and this is E1, E2, En. So let's write it in a matrix way, times E1, E2, En. So this is n by 1. This is 1 by n. So they are comfortable with each other, so we can multiply them. So we get 1 by 1, which is scalar. So this S is equal to, remember we define this as E, and this is E prime E, which from here we know that E is y minus x beta. Y minus x beta prime transpose times y minus x beta. And we want to minimize this quantity by choosing beta. And you should know that this objective function is a quadratic function. It's quadratic with respect to beta, the parameters. So it is well defined. It has a unique global minimum. Okay. So let's put a transpose inside. Y prime minus x beta transpose. Y minus x beta. So when we transpose two multiplication to matrix, we get B prime times A prime. That's the rules of matrix operations. So we get y prime minus beta prime x prime times y minus x beta. Let's expand this. So multiply this and this. So y prime y minus y prime x beta. Then this and this. Beta prime x prime y minus beta prime. So there's negative sign here, so actually it's positive. -1 times -1 is positive. Beta prime x beta. Okay, this is our S. Note that these terms is 1, okay, oops, beta. So y prime is 1 by n, x is n by k, then k beta is k by 1. So the multiplication, this one is 1 by k, then this k by 1, so this one is 1 by 1. So y prime x beta is actually a scalar 1 by 1 matrix. And similarly, this one is 1 by k beta prime x prime k by n y n by 1. So beta prime x prime y is actually 1 by 1 scalar. 1 by 1 scalar, so a transpose of itself of the 1 by 1 matrix, let's say, is the same. Okay, so beta prime x prime y transpose is equal to itself, which is beta prime x prime y, and we bring the transpose inside, so it's y prime x beta. So these terms is the same as these terms, so we can combine them. So our objective functions y prime 1 minus 2 y prime x beta, so this is the same, plus beta prime x beta. So we want to minimize this sum of square error by choosing beta. So first order condition, partial s, partial beta. And note that s is a scalar, but beta is k by 1 vectors. So when we partial s, we partial differentiate s with respect to beta. So now we are getting k by 1 vectors. This is equal to differentiate with respect to first element beta 1, then beta 2, then beta k. And this partial differentiation, for example, partial differentiate x with respect to beta 1, then that means we are holding beta 2, beta 3 until beta k as a constant. We treat them as constants. Okay, if you are familiar with the linear algebra, it should be easy for you to differentiate this one with respect to beta. So I'm going to give you the result, and then in case that you are not familiar, I'm going to show you why that's the case in more details. So the first term here, the first term of s does not depend on beta. So when you differentiate with respect to beta, it disappears. Second term is negative 2x prime y. Okay, we have y prime x beta. Differentiate with respect to beta, we get 2x prime y. You might be wondering why. I'll show you in a moment. And third terms, this is quadratic function of beta. So we are going to get 2x prime x beta. And you should be wondering why. If you are familiar, you should agree. If you are familiar with linear algebra, you should agree here. However, if you are not, I'll show you why. And this is for first order condition, set it to 0. Okay, let's see. Let's look at this term first. Let's call this term q. So q is 2y prime x, or we can drop the 2, that's fine. Just say y prime x beta. So this is 1 by n, this n by k. So y prime k is 1 by k, and beta is k by 1. So 1 by k, so let's suppose that we know that y prime k is 1 by k vectors. So let's say it is c1, c2, ck. Okay. So our q here, remember now we are treating this as this is q. So it's c1, c2, ck times b1, beta 1, beta 2, beta k. So this is just, again, so this is a rule of matrix multiplication. It's just C1 times beta 1 plus C2 times beta 2 plus CK times beta k, big K. And now partial Q divided partial beta is just partial Q partial beta 1 until partial Q partial beta k. And it's easy to see that this is linear function of beta. So partial Q partial beta 1 is just, there's a beta 1 here, so it's C1. There's no beta 1 in the remaining terms. Similarly, partial Q partial beta 2 is, there's a beta 2 here and no beta 2 in other places, so it's just C2. And partial Q partial beta k is just CK. So this is just C1, C2 until CK. And you should know that now this is the transpose of this. Okay, so this raw column k by 1 column vectors is a transpose of this 1 by k raw vector. So it's equal to, this is equal to y prime x transpose, and that's just x prime y. Okay, that's why we have x prime y here, and we have 2 here, which is constant, so it's fine, still there. Negative 2 still here. Okay, so now we see that differentiate these terms with respect to beta, we indicate these terms. Okay, let's look at the third terms. This term, let's call this term q. Let me erase this. Okay, let's say q. Now let q be beta prime x prime x beta, and know that x prime is k by n, x is n by k, so x prime x is k by k. And also note that x prime x is symmetric because x prime x is equal to transpose of x prime x. They are equal, so this is symmetric. So let's call this x prime x is a11, a12, a1k, a21, a22, a2k, ak1, ak2, akk. Okay, and note that because x prime x is symmetric, x prime x is equal to its transposition. That means a12 is equal to 1 or more general, aij is equal to aj. So this matrix is symmetric along a diagonal. Okay, so let's expand this multiplication. Beta prime is beta 1, beta 2 until beta k times, what is this? A11, A12, A1k, A21, A22, A2k, AK1, AK2, AKK times beta 1, beta 2, beta k. So this is 1 by k, this is k by k. So this multiply this one is we get 1 by k raw vectors. So let's multiply these three matrices. So this is this row times the first element will be this row times this column. So it's beta 1 A11 plus beta 2 A21 plus beta k A, so A12. Oh no, A21 AK1. So this row times this column, first element. Second element is this row times the second columns. So it's beta 1 A12 plus beta 2 A22 plus beta k AK2, so on and so forth. Last element is beta 1 times A1k plus beta 2 times A2k plus beta 2 times A2k, beta k times AKK. So this is 1 by k vectors. So let's time it beta 1, beta 2, beta k. So it's equal to, again, this row times this column, sum them up. So beta 1 times beta 1 A11 plus beta 2 A21 plus beta k AK1 plus beta 2 times this element, beta 1 A12, beta 2 A22, beta k AK2 plus the middle terms plus last terms beta k times beta 1 A1k plus beta 2 A2k plus beta k AKK. Okay, so we have all these terms. So we want to, and we call this Q. Okay, we want to compute partial Q, partial beta, which is k by 1 vectors. First element is partial Q, partial beta 1, second partial Q, partial beta 2, until partial Q, partial beta k. Let's compute the first one first. So partial Q, partial beta 1. So when we are doing partial differentiation with respect to beta 1, withholding beta 2, beta 3 until beta k, all the other betas constant, treat them as constant. So this first term, let's look at these first terms here. There's a beta 1 here, so differentiate. So now we need to use these chain rules in calculus. So we get beta 1 A11 plus beta 2 A21 plus beta k AK1. Then we have a beta 1 here, right? We have beta 1 here, which is beta 1. So when we differentiate with respect to beta 1 inside the bracket, we get A11. A11 times there's a beta 1 outside the bracket, so it's still beta 1 A11. And there's no beta 1 in here, so we can ignore them. For the second terms, there's a beta 1 here. You want to note there's a beta 1 here. Okay, so and no beta 1 for other terms. Okay, so we can ignore them. For the third terms, there's a beta 1 here. You want to note there's a beta 1 here. Okay, so and no beta 1 for other terms. Okay, so So differentiate with beta 1, we get A12, and there's a beta 2 outside the bracket, so we get a beta 2 A12. Similarly for other terms until the last term, which is beta k A1k. And now you should know that A11, A21 is the same as A112. AK1 is the same as A1k because this matrix x prime x is symmetric. So this is add these two up. This is actually equal to 2 times beta 1 A11 plus beta 2 A21 plus beta k AK1. Okay. Okay, maybe let me write it here. So partial q partial beta 1 is 2 beta 1 A11 plus beta 2 A21 plus beta k AK1. Okay, this work out the beta 2. And so let's check the second terms here. So because we are differentiating with respect to beta 2, this one. So there's a beta 2 here, so we get a beta 1 A12, beta 2 A22, and so on and so forth until beta k AK2. Now look at the first terms. There's a beta 2 here. Beta 2 here. Differentiate this one with respect to beta 2, we get A21. A21, we have a beta 1 outside the bracket, so we get beta 1 A21. Okay, that's for these terms. For these terms, inside the bracket, there's a beta 2 here. So differentiate it with beta 2, we get A22. There's beta 2 outside, so it's beta 2 A22. So on and so forth until the beta k, these terms, we get a beta 2 here. So which is beta k times A2k. Also know that now so 2 1 2 2 2k, I don't need this one. No, A12 is the same as A21. A22 is same as A22 here. AK2, A2k, because the matrix is symmetric. So these two terms are actually the same. So we can write here partial q partial beta 2 is 2 beta 1 A12 plus beta 2 A22 plus beta k AK2. Okay, similarly for the other terms until the last term beta k, we get 2 beta 1 A1k plus beta 2 A2k plus beta k AK. Okay, so this we computed these k components of this vector. Let's stack them together. So that we can denote them in a more compact way. And you should know that now we have a common term 2. So we have we have 2 appears in each component. So we can actually pull it out. So partial Q, partial beta is 2 there. We have beta 1A11 plus beta 2A21 plus beta K1. Then beta 1A12 plus beta 2A22 plus beta K2. Beta Ka1K plus beta 2A2K plus beta Ka. And we can factor out this K by 1 vector as A11, A21, AK1, A12, A22, AK2, AK1, AK2 until AKK times beta 1, beta 2 until beta K. And note that A12 and A21 are the same, so let's change this to 1, 2, 1K. It's 1, 2 to be 2, 1. K. This is same as K. K1 is same as A1K. 2K until KK. And this is just x prime x. So we get it 2x prime x beta. Okay, I hope now it's clear what is 2x prime x. So first order condition, we have we choose beta to minimize sum of square residual, which is y prime y minus 2 y prime x beta plus beta prime x beta. First order condition, partial S partial Q is equal to 2x prime y plus 2x prime x beta is equal to 0. This implies that, sorry, there's a negative sign here. 2x prime x beta is equal to 2x prime y. We can cancel out the 2 on both sides, and then now we need this matrix x prime x, which is k by k matrix, to be invertible, full rank. And that's why one of our assumption is that there's no multicollinearity. So if there's a multicollinearity, then we cannot invert this matrix. Okay, so x prime x multiply both sides on the left, but it's inverse. And this becomes I in the identity matrix of K. And identity matrix modify any beta, we still get beta. So we get beta is x prime x inverse x prime y. And we are going to put hat on top of it to denote that this is the estimator, OLA estimator. Right, so we have an estimator for beta, and remember we also have another parameter which is sigma square. We say that, okay, EI conditional data is normally distributed, which means zero variance sigma. And remember we also have an E, which is E1, E2. We stack all EI together on top of each other. So we get En, so this is vector, n by 1 vectors. So now E is actually normally distributed, which means so this 0 is a vector. Each component k by 1, n by 1 vector, where each component is 0. And this is called valence covariance, which this is called sigma. What is sigma? Sigma is now n by n matrix. So is variance of E, valence covariance matrix E, which is equal to E prime. Okay, this is expected value of E times E prime. So E we know that is E1, E2, En times E1, E2, En. So this is n by 1 by n. So after the multiplication, we get n by n matrix. E1 times E1, so E1 squared. E1 times E2, we get E1, E2, and E1, En. Then E2, E1, E2 square, E2, En. En, E1, En, E2, En square. Okay, so we can take the expectation inside. Expectation is a linear operators. Okay, so it's E1 square, E1, E2, E1, En, E1, E2, E1, E2 square, E2, En. We have En, E1, En, E2, En square. And remember, our assumption is that we have one assumption is homoscedasticity assumption. So EI square, which is variance of EI, which is sigma square. That's homoscedasticity. Also, we also assume that there's no correlations. So EI, EJ, 0. That implies for I not the same as J. So now we see that of this n by n matrix, which is called sigma, on the diagonal element is sigma square. The off diagonal element are all 0. Here, and we can write it. We can factor out this sigma square times what is called n by n identity matrix. So this n by n identity matrix is one only diagonal 0 in other places. So this is n by n dimension. So sigma square. So this E actually is normally distributed with mean 0. Valence covariance matrix In. Okay, so we see that sigma square is EI square. And given this, observing this, the estimator, one natural estimator of sigma square is this called sigma hat square. It's just sum this particular residual. So EI hat is just theta y high minus yi hat, which is yi minus beta hat xi times xi prime beta hat. Remember, beta hat is our OLS estimator. We have formula here. We derive a formula. This. So sum this square them E hat I square, sum them up. So now, okay, what we want is we want to get average, but we are not dividing by n, but n minus k. This is because when we are computing this residual, predicting these residuals, we are fixing this beta hat, which has k element in it. So we lose k degree of freedom. That's why we take k away from n. And if you still remember, in the simple regression model, we take n minus 2 because there we have b1, b2, we only have 2 parameters. Now we have k parameters, so we divide it by n by k. So this is the estimator for the sigma hat, the variance of the random error. Okay, let's look at finite sample properties. Okay, we said that beta hat is blue estimator, BLUE. This is called Gauss Markov theorem. It's blue. B means best. It has beta hat has, and bear in mind that beta hat now is k by 1 vector. It's a random vectors. Has the smallest variance, and beta hat is a function of data, so it's beta hat is a random variable, okay, random vector actually, among the class of unbiased linear estimator. That's what it means at best. Linear, L means linear, but we won't prove this, okay. Linear means, this is easy to see because beta hat is x prime x inverse x prime y. It's a linear function of y. So it's linear. Thirdly, U means unbiased, which means expected value of beta hat is actually equal to true value. In order to see this shows this equality here. So we know beta hat is x prime x inverse x prime y, and our model is y is x beta plus e. Okay, so let's plug this one into here. So which x prime x inverse x prime x beta plus e. So we have modified inside x prime x inverse x prime x beta plus x prime x inverse x prime x inverse x prime e. So this and this inverse, this and its inverse. So when we modify a matrix with its inverse, we get the identity matrix. Identity matrix times beta, we get beta. So this is beta plus x prime x inverse x prime e. So now we can write beta hat as true value beta plus a terms. And let's take expectation on both sides. So expected value beta is constant, is not random variable. So we take expectation is still beta plus expectation these terms. Prime x inverse x prime e. And now we want to use what is called law of iterative expectation. So basically it says that, okay, E, say this is called A. Take A is a random variable. This is A and B, they are random variables. So what I can do is expected value A is, I'm going to first conditional B, then taking expectation with respect to B, so they are equal. That's what we call law of iterative expectation. So the inner expectation is conditional on B. The outer expectation is taken over the B. So this will be the same as expected value of A. Okay. So let's the outer expectation taken with respect to X. Inner expectation take conditional on X. When we conditional on X, essentially we are saying that we treat X as kind of constant. So we can pull it out, the expectation. So this term, this is constant now. So we get this. Pull it out of inner expectation. So it's x prime x inverse x prime e x. And by our assumption, the strict exogeneity assumption, so this is equal to 0. And 0 times a terms here, we get 0, right? So the whole terms is actually equal to 0. So now we show that expected value beta is equal to beta. So indeed, our estimator is unbiased. Okay, let's look at large sample properties. So now we are interested in two things. First is consistency. This means that beta hat, as sample size goes to infinity, should converge in probability to true value beta as in goes to infinity. Or in other words, as sample size increase, the probability that beta hat will be far away from the true value becomes smaller. Okay, now let's prove this. So we have beta hat is equal to beta plus this x prime x inverse x prime e. And I'm gonna do this trick. Divided this by n, x prime x, then times by n raised to the power -1. So this is equal to beta plus 1 over n x prime x, and n raised to the power -1 is 1 over n x prime e. And these terms, and these terms, we are going to use law of large number to look at the limit, to look at where do they converge to in the limit as n goes to infinity. Let's look at this term first. So x, remember x is x1 prime, x2 prime until xn prime, right? So x prime is just x1, x2, xn, and each x1 is k by 1, okay, and we have e1, e is e1 until en. So 1 over n x prime e is just 1 over n sum from 1 to n xi E. Okay, so now we see that this quantity is actually average of in IID random variables, right? We can apply this low or large number. Low or large number says that this actually converges in probability to its mean, and this by law of iterated expectation, we can show that is equal to and then pull this xi out. Conditional whole x here is the whole x1, x2, x until xn. So we can move this xi out, and we know that this is 0. So this is actually 0. So we show that by law of large number, this converge in probability to a term 0 disappear. Now we look at this term. Let's look at these terms. So similarly, we can write x prime x as an average. So remember, x prime is x1, x2, xn. X is x1 prime, x2 prime, until xn prime. So x prime x is equal to sum of at 1 to n xi prime. Okay, xi prime. Bear in mind that this is in k by 1 by k, so it's k by k matrix. And again, this is this random variable, they are IID. So low or large number says that as n approach infinity, it converges to this. And let's call this A. And we need A, this k by k matrix, to be invertible. Or in other words, it's of full rank if you know more about this linear algebra. So we have -1 here, inverse here. We can invert them. But anyway, we now show that see that by law of large number, this converge in probability to beta as in the true value of parameter as n goes up to infinity. So we call this consistency. Beta hat is a consistent estimator of beta. Okay, let's look at asymptotic normality. So we know that beta hat is equal to beta plus x prime x inverse x prime e. And now we're going to write this in this rewrite this equation in this way: beta hat minus beta, which is equal to x prime x inverse x prime e. Previously, a moment ago, we said that this converges in probability to 0. So actually, the whole terms actually converge in probability 0. Or in other words, the variance of these random variables actually converge to 0. Kind of collapse, degenerate. So let's scale it a little bit differently. Let's time these terms by root n. So now we have root n here. Or we can write it as 1 over root n x prime e. And these terms, we already see that this converging probably to A, okay, which is k by k full rank matrix. We can invert it. And let's look at root n. So which is x prime e. This is the same as root n. Sum. We show that we show that this x prime is x1, x2, xn. E is times E is E1, E2, En. So it's xi, ei. Okay, so now we are going to apply another important theorem, central limit theorem. This would say that this converge in distribution to a normal random variable with mean ei, which is 0. Okay, by our assumption is 0. Variance xi, ei. Okay, let's calculate what this variance is. So this, note that this is actually k by 1 vectors. So the variance of this is e xi, ei times xi, ei prime. So k by 1, 1 by k. So we get k by k. So this is e xi, ei prime, xi prime. So this, and now this conditional on x, so we can pull xi out. Previously, we calculated this as, remember, is, okay, this is just the variance of ei. So we get xi sigma square. Okay, this sigma square is a constant. Okay, it is a scalar. So sigma square xi prime. So the variance of this is actually okay, let's calculate. So let's calculate this. This is just 1 over n, and this is IID, so it's sum of and we see that this is sigma square this one is sigma square xi prime, so which will be sigma square 1 over n 1 n sigma, there's no, okay, we already put it out, xi prime. So this is just, this one is just 1 over n x prime x. And as n goes to infinity, this we know converges to A. So now the variance of the whole list is sigma square A. Okay. We're almost done now. So now we show that these terms converge in distribution to a random variable with mean 0, variance covariance matrix sigma square times A. So, but we have, so for this term, we want the limited distribution of these terms. So there's an extra terms here, which is A. So we actually can show that given this, we can show that root n beta hat minus beta converge in distribution of to mean 0 variance would be the variance of the whole terms here. The variance of this one is just a minus 1 sigma square a minus 1. This cancel out. Okay, so it is sigma square a minus 1. So that's the limit distribution. Okay, so it's asymptotically normal. We see that.